Math 3, but you might still have a little bit of hard time answering that question, okay? A logarithm is the power to which a number must be raised in order to get a certain value. So if we think of it like an exponential, 2 to the x power equals 16. This x right here is what we're doing when we're finding that x is what we're doing when we're doing a logarithm. So this x right here would be the base 2 logarithm of 16. That would be written like this. Oh, I gotta get my pen here. That would be written like this: log with a base of 2 of 16. And so what is that? What is the x in that case? It would be 4, right? I have found the very, very, very best way for you to think about logarithms is it's just the inverse of an exponential. Okay, inverse of an exponential. In fact, that is the way I teach it. I don't really teach the rewriting rules. I teach it as inverse of an exponential. And kids usually do pretty well with it. So if I have something here, I've got like 2 to what power equals 1024. This is the base 2 logarithm of 1024. So whenever you're thinking about seeing like log base 7 of 10 of something, right? The base number is the number you're raising to a power, and the number you're taking the log of is the answer for that. In fact, this was a question on Quiz Bowl Saturday, and I think it was 4 to the x power. I think it's 10. Is this 10? 2 to the 10th power? Somebody check it there. Calculator. 2 to the 10th. Yep, it's 10 for that. Okay. Logs are used in a lot of context. I wish we had more time to explore this a little bit more, but we will see some applications. We won't get to do nearly as much as I would like to with this. But logarithms, one of the top things that you're going to see logarithms used for that kids are usually familiar with is the Richter scale. Although whenever I was looking this up, I discovered that we don't use the Richter scale anymore. In fact, I learned that the Richter scale has been replaced by the moment magnitude scale, which is what they use whenever they are classifying how intense an earthquake is. However, most people still call it the Richter scale, even though it's not really the number that they're using anymore. Both of those, however, are logarithmic scales. What this means is each jump in a level in the Richter scale is not like going up by 1. It is multiplying by 10. So a few years ago, it's probably been longer than I realize now, we had that earthquake in Sparta and you could feel it here. So that earthquake was was it like a 4 or 3 or something? It was, I want to say it was like a 4. So if you have a 5, it is 10 times worse than a 4. If you have a 6, it's 10 times worse than the 5. That means it's 100 times worse than the 4. So living through being a survivor of the Sparta earthquake is nothing like being the survivor of a 6 or a 7, right? Or especially an 8 or a 9. Because even from a 7, which is going to be pretty bad, you're going to have some pretty significant damage with a 7. 7 is still not, a 9 is 100 times worse than a 7. So it's a logarithmic scale for that. The decibel scale also works that way. So it's for sound intensity. We had a problem that was talking about decibels earlier. So whenever you go, I think decibels, it's from 20 to 30. is actually multiplied by 10, and then 30 to 40 would be multiplied by 10 again. So like from 20 to 40 would be 100 times more, 100 times louder for that. Logarithms are used anytime you have data where you're dealing with really, really big numbers. I know that one place I first saw this was back during COVID, because as a math teacher, you know, they tracked those COVID numbers like crazy. They were always talking about COVID numbers. You go on different websites, look at the graphs. So I found that very interesting, just mathematically, to see like what was going on. And on one of the websites that I would check pretty often, they had an option where you could turn your graph from a like regular graph to a logarithmic graph. Because what happened is those numbers like skyrocketed, right? So the numbers got so big, it was really hard to see patterns in what was happening early, because it just looked like a flat line, and then it shoots up really fast. So it's really helpful in data analysis whenever you're looking at really large numbers, or really any other instance where you're dealing with really large numbers. Those are all places where logarithms come into play. Logarithms are used in a lot of places. Probably nobody uses logarithms in their daily life to balance their checkbook and, you know, live out their regular life. But in a data analysis sort of scenario, they're really important for that. So there are jobs that use this a lot. So a logarithm is the inverse of an exponential. I don't know what that just did. Exponential function. Okay, so just like addition and subtraction are inverses of each other, exponentials can be rewritten. So I believe probably in Math 3, you kind of memorized these formulas and used them to translate between exponential form and log form, which works, and you're welcome to keep on doing it. I'm really not very picky about like the way that you think about these things or show your work on these things. What I like to do is teach these as inverses of each other, which will mean that your like sides of your equal sign will be switched. If you do it my way, your sides of your equal sign will be switched. If you do it just the formula way, there'll be a different way, but it's still the same problem. So when we have b to the a equals c, that b right there is our base of our exponent, right? Because it's the base being raised to the power. That base of the exponent becomes the base of the log. And then a and c, here a is your exponent, c is your answer. Over here, c is going to be your value, a, the exponent, goes over here. So you can kind of just remember like where everything goes in that formula. But the way I like to think about it is as an inverse. So it is important to note that log base b of b equals 1. And b to the log base b of 1 equals 1. What this means is that a log, when you take log of something that has that same base, they cancel out and equal 1. If you have a base raised to a power that's a log that has that same base, they cancel out and equal 1. So if I have log base 4 of 4, log base 4 of 4 itself is going to cancel out, and I'm just going to get 1 for that. Now 2 is a little bit different. 2 and the log base 2 cancel each other out. You're going to be left with what's in the parentheses, right? So we would get 5 for that. So if that's the case, look at 3. What do you guys think we get for 3? as going to be x plus 5. Okay? So I will show you both ways of thinking about this to rewrite exponential and log equations. So you know that b to the a equals c can be written as log base b of c equals a. Right? That's that formula we had on the other one. So you can just identify your pieces and rearrange them. So like for example 4, 5 is my base. So I'm going to have log with a base of 5. The exponent goes over here on the other side of the equal sign. And the number that it's equal to is what you're taking the log of. Make sure that 5 is a subscript. It should be small and a little bit lower. The 25, sometimes you will see parentheses around that 25. Sometimes they won't put them there. It could go either way for that. Okay, I do this just a little bit differently. The way I think of example 5 is I've got 8 to the 3rd power equals 5 to the 12th. If I do not want this to be an exponent anymore, I want it to be a log instead. This is the way I think about it. I think of doing log base 8 of this side and log base 8 of this side. So I'm right. I usually do it in my head, but I'm writing it out so you can see my thoughts. Log base 8 of 8 to the 3rd is going to equal log base 8 of 5, 12, right? It's legal to do something to one side as long as we do that same thing to the other side. But what happens when I do log base 8 of 8 right there? Those cancel each other out, right? So 3 equals log base 8 of 512. It's going to be the same as if you did the, it's going to be the same as if you just rearranged using that formula, but this type of thinking makes it a little bit easier when we get to the equations. So when we start doing equations with this, I think that makes it a little bit easier. My side, like I'm getting 3 equals log base 8 of 512. A lot of times the answer choice will look like this, log base 8 of 512 equals 3. The sides of the equal sign can just switch. It doesn't matter for that.
So for this, you're just solving for the exponent?
Yep, for this, because if you don't want it to be an exponential anymore, and they're asking us to write it in logarithmic form, so that means we don't want it to be exponential anymore. To get rid of the base on the exponent so it won't be an exponent anymore, you just log with that base. So like right here, the way I think of this is I think in my head, I'm doing log base 6 right here, which will cancel, and then log base 6 of this side right here. So I would get x equals log base 6 of 125. It's okay, of course, to say log base 6 of 125 equals x also. Good here. All right, so for 7, we're going from logs to exponentials, so it is perfectly okay to say, oh, well, 5 is my base. So if I'm writing this as an exponent, 5 has to be the base that's raised to the exponent. So that exponent will be the 4, and that will equal what you're taking the log of, which is 625. So you can just kind of use the pieces and put them in the right place in the puzzle. But what I like to do with this, because you don't have to like think about the pieces of the puzzle as much. What I like to do, if I have a log base 2 and I want to get rid of it, I'm going to do 2 raised to that power on that side. And then that means I've got to do 2 raised to that power over here. Now be careful, you're not raising it to the second power. You're doing 8 equals 2 is the base, 3 is the exponent there, right? We're not doing 3 squared. We're doing 2 raised to that power right there. Same thing you'll get if you just rearrange a puzzle. That'll work fine as well. So like if I want to do number 9, I want to get rid of that log with a base of 7. I'm going to do 7 raised to that power. It'll just cancel that side out. I'm going to do 7 raised to that power over here. So x is going to equal 7 to the 10th power. Make sure you get that in that right order. The base of your log has to be the base of your exponent on the other side. Okay, so just being able to rewrite is something that we'll practice because you have to be able to do this to do anything that's harder after this. So let's keep going. There are a couple types of special logarithms that have their own special symbols and names. The first is called the common log. If you ever see a log without a base, then it is assumed that that base is 10. What I find a little bit odd is it appears that on the AP exam, they always write it as log base 10. They don't write it as just log x. And all of the like pre-cal curriculum stuff I've seen before never did that. But on AP calculus stuff, it looks like they put the 10 there as the base. I don't know if there's some countries that do that differently and they're trying to accommodate for that because they give that internationally. But if you see it without a base, assume it is a 10. Okay, that's called the common log. And then you also have natural log. And natural log is a log with a base of e. Okay, so if you see natural log of x, it is a log with a base of e. You have these buttons on your handheld calculator. So there is a button that just says LOG right there next to your 7. And you have an LN button right there next to your 4, right below that LOG button. So there are buttons on the calculator for this. You can also just type them into Desmos as well for that. Or I'm sure there's buttons for them somewhere too. So if we have to rewrite each equation here in the opposite form, these can be just a little bit trickier because they don't have the base shown for them. So what I like to do is I like to go over here. Let me do that. And like just write it in. The base on that is 10. So if I want to rewrite this in exponential form, if I have a base of 10 on my log and I want to get rid of it, I'm going to do 10 raised to that power to cancel out that log on this side. And if I do that right here, I got a 10 raised to that third power right there. And so on this side, I've just got my x left. On this side, I've got 10 to the third power. And you'll notice that like solved that equation right there. 1,000 would be your x. For natural log of 4, this is a base of e. I like kind of writing that in even though it's not necessary. So if I want to get rid of a log with a base of e, I'm going to do e raised to that power on both sides. So the e and the natural log cancel each other out. You're just left with the 4. Over here, you've got e to the x power. Okay, remember that e is a number. It's 2.71828 something or another there. So it's just kind of like pi. It is a number. It's not a separate variable. So e to the x equals 5. This one is an exponential. How do we get rid of exponentials? Logs, right? So like if you want, you can write log with a base of e. It just makes you look like you don't know what you're doing a little bit, right? Because a more refined person would write ln for that. But it is a log with a base of e, so it's mathematically correct to write log base e right there, which cancels out that e. But nobody really, like, if you leave your answer as log base e of 5, it looks like you don't know what you're talking about because log base e is just natural log of 5. So this is what you would see, like, on answer choices there. But it does help some kids to, like, actually write it as log base e for that. Okay, we're good here? Okay. Evaluating log expressions without a calculator. We have a fairly large number of questions on our exam that are not calculator active. So they might put some log questions on the calculator inactive section. If you want to type this into the calculator, you go over to Desmos, you tell it There's a special button for logs, but if you do log and you do shift underscore, like if you're going to type an underscore, it'll take you down here, log base 2 of 8. It'll do it for you, right? So you could type it in like that, or there's a special button for it if you go over here under functions, somewhere. Maybe right there. You want that log with a base of A. It's easier to do that underscore thing quicker, but that will work right there. But a lot of times this shows up on calculator inactive, in which case that is not helpful to you. So I'm going to show you 2 different ways that you can analyze these. Okay, so the first is to rewrite it as an exponential. Okay, so if you rewrite it as an exponential, I do not know what this equals right now, but I'm going to call it x. So if I rewrite this as an exponential, then 2 raised to that power will get rid of my log, which means I got to do 2 raised to that power on the other side. So 8 equals 2 to the x power. And then I just have to think about what would I raise 2 to that would give me 8. So what is the value of that x right there? 3. So that x would be 3. So log base 2 of 8 would equal 3. So rewriting as an exponential is an option. Another option though that I'm afraid you might see more often here is rewriting it with the base. So like if we look at 14, what is the base on that? There's not one written. It's 10. This is a common log. It's understood that that's a 10. So rather than rewriting this one as an exponential, which will also work, I want to write this as log base 10 of 10 to some power, right? 100 is 10 to what power? 2. Okay? 10 squared equals 100. So if I write it like this, what happens when I got a log base 10 of 10 to a power? Those cancel each other out, right? Because if I do a log of an exponential with that same base, they cancel each other out. So I just get 2 for that. What I'm worried they might do to you is they might not ask you for the answer to that question. They might ask you for the setup for the question. They might ask you, which one is equivalent, and then rather than having the answer, they might have log base 10 of 10 squared or something like that. Yeah. It doesn't. You can do it either way. Okay, now 15 is a little trickier right here, because either way it's going to be a little bit trickier, because if I rewrite it as an exponential, I've got 16 to the power, 16 to the power, so 4 equals 16 to the x power. And then if I rewrite it over here, log base 16, if I try to do it this way, 16 to a certain power right there. Either one of these is a little bit trickier because it's not easy. The numbers are not quite as easy. What do you guys think right here? Okay, 1/2. All right, because 1/2 is the same as doing what? A square root. So if I do 16 to the 1/2 power, that is equal to the square root of 16, which is going to give us 4. So I will get 1/2 for my answer here. Or I could write this as 16 to the 1/2, which is going to be the square root of that 16.
When you go to write your final equation, do you need to put the log notation, or do you just put x equals?
It's in this case they're just asking you to evaluate just 1/2 as your answer. You don't even have to put the x equals because we kind of added that in to rewrite it as exponential. You would just say what we're saying here is that log base 16 of 4 is 1/2. They're equal to each other. Like we could, if it's calculator active, we just type this stuff in and get the answer, but it's not. All right, so like let's try to do it this way in case they log base 3 of 3. I got to put some power right here. What am I going to have to put there? It's going to be 0. Right there. Because what is 3 to the 0 power? It is 1. No, because the cube root of 3 is not like dividing by 3. It would be what number times itself equals 3. So like 1 times 1 times 1 does not equal 3 for that. So we would not be able to do 1/3 for that.
So they could either do it that way or the
Right. Or they could have said 3, 3 to the power. So like 3 to the x power equals 1, and then you're trying to think about what number that would be. Okay, now, did I put it on the next slide? No. Okay, let's make ourselves a note right here. Log base b of 1 always equals 0. Okay? Does not matter what the base is. Okay? So, if you're doing any type of log of 1, you're going to get 0. The reason is because the only way you can get 1 with exponents is to have an exponent of 0, right? So it doesn't really matter what the base is for that. You won't ever see a base of 0. That would just be like undefined. That's not going to be something that you're going to see. All right. We also need to know our change of base formula. So the change of base formula is that log base b of a equals log a over log b. Okay, so this can be helpful on your calculator just to like speed you up a little bit, because you can. Remember, last year I was having to teach them how to do it all on this calculator, so it wasn't allowed on the exam. The AP has been paper pencil for a very long time because those free response parts, but because of a big cheating scandal, they are moving almost all of their tests online. Because what was happening is they were mailing the tests to the school districts like 2 or 3 weeks before, because you have to have them the day of the test, and apparently some students were somehow gaining access to those. So there, probably somebody at the central's office's kid was in Precal, or it wasn't just Precal. It was more than one subject, I think, and they somehow got a copy of the test before they were supposed to get the test. So with that being online, you'll still write your free response part on paper, but nobody gets the test till the day of the test because you just have to have access to it on the computer. So that hopefully will fix any issue they had there. And there's the big plus for us is that means we get to use Desmos on the test. But if you want to know how to do this on this calculator, you're going to click Math, and there's a log base that's on there. Or a lot of times, even in Desmos, I will use change of base formula because log base 3 of 5 could be written as log 5 divided by log 3. You don't have to do this now that we have Desmos, because in Desmos, you could just do, if you do log base, what was it? Was it 3 of 5 or 5 of 3? 3 of 5. All right, so log base 3 of 5, you can just type it in like that. But if I do log 5 divided by log 3, I don't have to use any special keys or anything. It gives you the same number there for that. So because we can use Desmos, that's all I'm going to do with this one right here for right now, because it becomes less important. They could still use it on some questions that they ask you about.
Wait, do we need to find like the answer for these, or are we just?
When it says evaluate, it just wants you to give the like decimal approximation for it. So, so you're just given like the decimal approximation. Okay. This one asks us which tables show an exponential pattern. Okay. So, if we look at this, let's rule some out, because there should be some here that, actually, we should already be able to do this. Look at it real quick. Which one's exponential? This is not asking for logarithmic. This is exponential. Okay, it's that third one. Right? This one just adds 2, adds 2, adds 2. That's linear. This one, you add 1, then you add 2, then you add, I'm sorry, we add 1, we add 3, we add 5. If you do a second difference, you add 2. That one's quadratic. Right? With an exponential, we're looking for the x-coordinates to be, the y-coordinates to be multiplied by a number. Right? So that would be an exponential pattern. That's already something we know how to identify. So, exponentials and logs are inverses of each other. So, so use the table of h below to make a table for the values of the inverse of h. So what do I do in a table if I have an inverse? Just got to switch them, right? So now I've got 1, 2, 4, 8, and 0, 1, 2, 3. So logarithmic tables are going to be a little bit different in how we look at them than all the other ones we've looked at before. So in an exponential function, the input values increase in, might have to look. It's going up by the same amount each time is what it means. But I think it's equal intervals. Yeah, equal intervals is what I mean for. And the output values increase proportionately. And proportionally means multiplying by a number. Right? So it would make sense if the log is the inverse of the exponential and we switch our x and y's, it pretty much just switches those two blanks right there. In a log function, the input values increase proportionately. And the output values increase in equal intervals. Okay, logs are really the only ones where we're looking for our x's not to go up by the same amount. Okay, so if we look at this next table, we want to determine if we could have logarithmic, exponential, or neither. So, what we're looking for, if we have exponential, we got x values increasing by a constant amount, y values are being multiplied by a number. So this first one, what do we have for it? That one's going to be exponential. Okay? Because you are multiplying by 1/2, right? To get to the next line. Okay? Logarithmic is different. We want to see almost that same thing happening, but in opposite columns, right? So what we want to see is like we see in 22. We go up by 10, up by 10, up by 10. That would make you think it's linear, but your x values increase by the same amount as well. They do not. The difference here, this goes up by 20, and then we go up by 60, and then we go up by 180, I think. Now, 10, I'm not multiplying. It's like, actually, I guess I am. I could look at the pattern, or what are you multiplying by there? It is times 3, right? So your x's are being multiplied, your y's are being added. This is logarithmic. Okay, what about 23? That one's neither. Why is it neither? Right, x and y values are being multiplied. So I'm not sure exactly what that is, but it's not what we're looking for exponential or logarithmic. I don't even know if it has like a name to it or not. I'm not sure. 24. What about that one? That one is logarithmic because the y values are going down by 3, constant rate of change on our y values, but our x values are being multiplied by 2 for that. So that's what logarithmic's going to look like. Does that make sense on those? All right, let me see what else I got left here. All right, let's do this slide. Let's do this slide, and that's going to be as far as we can get for today. So, if I'm asked to find the inverse of a function, okay, what do? I switch my x and y. I solve for my new y, right? So let's do that for this case. That right there is like your y. So you're going to have x equals log base 7 of y. How do I get rid of a log base 7 right here? 7 raised to that power. We'll cancel that out, which means I have 7 raised to that power over here. Make sure you got 7 to the power, not x to the 7th. So I get 7 to the x power equals my y. So f inverse of x is 7 to the x power right there. If I do that same thing over here on 26, this is my y. So I'll have x equals 3 to the y power. This is where kids like really mess up because they want to divide by 3. But this is 3 to the y power. It is not 3 times y. How do I get rid of a base of an exponent? That's where I log right here. So I'm going to log base 3 here to get rid of that. So I got a log base 3 of x over here on the other side. So I get log base 3 of x equals y. So they'll probably write that with inverse notation for that. The next two are a little more complicated, and we are out of time, so we're not going to be able to do those. That probably means I'm going to have